Great. All right. Well, thank you very much, and appreciate everyone taking the time on a very hot, I guess, second day of summer. I was talking with Andrew, and I think he said there were some records broken yesterday. I think in the region. So I think this is, I guess, probably an opportune moment to have this discussion. So. I'm Andrew Lee, President and co-founder of InnoviaGEO, and we're focused on decarbonizing heating and cooling from the ground up. And so for this presentation, there we go. Just objective-wise here, really want to share knowledge and information about geothermal HVAC systems. Some of you may be familiar, may not be familiar. So that's part of our goal, is to spread the word about a great technology that's extremely efficient and unfortunately not well understood. And I think part of it is because it's typically buried in the ground, so we don't see it too much, as opposed to solar panels and wind farms. So throughout the presentation here, I'm just going to give that quick background on geothermal. I'll share about our new approach that we're taking to really make geothermal more accessible and affordable. Share some details about the pilot project we've done with Waterloo North Hydro as the host of that project, and some really interesting results we're getting through our testing, and then applications for our technologies and our next plans and steps. But to start off, just wanted to go through the scale and understanding of what it's going to take to actually decarbonize heating and cooling. A lot of times we're focused on the decarbonization of the electricity grid, decarbonization of transportation. Heating and cooling is not really talked about much. But when we actually look at our household energy use, the vast majority of energy we use is actually for heating and cooling. And so in North America, on average, about 70% of our household energy consumption is heating and cooling. So that's space heating, space cooling, and hot water. So it's the vast majority of energy we use in our homes. And in Canada, sort of the further north we creep up, the higher that percentage gets because of our need to stay warm in the cold winters. Although on a day like today, it's hard to imagine we have those winters still. But things are really starting to change. We've definitely noticed it, the past year and a half, where policies and cities, municipalities, provinces, whole states in the US and even countries are setting real policies now and targets to actually decarbonize heating and cooling, and setting defined timelines to do that. But what does this mean? So how does this compare with other industries that are decarbonizing? And so roughly speaking, the amount of energy that we need to transition to decarbonize heating and cooling is about the same as the transition to electric vehicles. So that's the scale that we're talking about, and that's pretty enormous. And so I think it's part of the conversation that we need to start having a bit more of, and how we can accomplish this energy transition. And so with that in mind, I want to share sort of one of the big solutions that could be a big part of that, and that's geothermal. And so geothermal systems provide renewable heating and cooling with zero direct emissions from the very ground you're standing on. And so they work under the same principles as your everyday air conditioner or fridge, by using electric heat pumps to move heat between a building and the stable temperature of the ground. So in the wintertime, heat is moved from the ground into the building to warm it. And in the summertime, the process is reversed, and the building is cooled by moving that heat from the building into the ground. And an analogy I like to use is you've experienced and used geothermal before. If you've ever walked into your basement on a hot day like today, that ground temperature is stable, and so when you walk into your basement, you feel you're immediately cooler because of that. And the efficiency of geothermal is what really changes the game. And it's because we're moving heat and not burning a fuel. So ground source heat pumps, exactly as they say, they're pumping heat from one place to another. And so typically a geosystem can be about 4 times more efficient than a conventional heating system. And up to about 100% more efficient than air source heat pumps, which an air conditioner is just a form of an air source heat pump. And so because they're so incredibly efficient, A geosystem can single-handedly cut your energy use in your building or home up to more than half, and your carbon emissions as well, and all at the same time saving you money because of that efficiency. And so where does that efficiency come from? And so it's all about that stable temperature of the ground that I mentioned here. And so what I'm showing in this figure here on the right is the ground temperature across a year by different depths from the surface. And so this purple line here, we see, it fluctuates quite a bit because we're close to the surface there. And so in the winter time, we're getting below zero, and then in the summertime, we're getting to above 20 degrees Celsius. But as we get deeper into the ground, that fluctuation through the year, we see it get less and less. And then by about 30 feet deep, that fluctuation is pretty minimal, and we're at a stable ground temperature all year round. And if I zoom into this figure here, I haven't found a good one in North America, so I have to use the one for the States. So it's in Fahrenheit as well, but we see where we are located here. So that stable ground temperature by that 30-foot depth is about 9 to 10 degrees Celsius across the year all around our area here in southwestern Ontario. So that's where the efficiency comes from. And so kind of the way to think about it is similar to if we're pumping water, up a hill, the higher it is, the more energy it's going to take to be able to pump that water there. And so the same principle applies with a heat pump because we're moving that heat, we're pumping that heat from one place to the next. And, if we go by the target of, 21 degrees Celsius, kind of room temperature of what our target is, in the wintertime, we're using geothermal, which is the ground is around 10 degrees Celsius. And so it's a lot easier to get heat from that 10 degrees Celsius and pump it into the building than it is, let's say, from the outside air if it's minus 20 on a cold winter day. And so similarly in the summertime, if we're cooling the building with the ground at 10 degrees Celsius, it's extremely efficient and easier to do and will take a lot less energy than if we're trying to move that heat when it's, just like today, over 30 degrees outside and pretty hot. So that's where that efficiency comes from. So if geothermal systems are so efficient, then why don't we see more of them? Why don't we see them everywhere? And why don't we see them, being the norm? And while the catch is, and the reason why is that the conventional way of installing geothermal systems can be costly, time-consuming, and messy. And so the process involves drilling small plastic pipes up to 850 feet these days. And those pipes circulate a fluid that exchanges the heat with the ground. And so although a geothermal system is extremely efficient, the payback versus conventional HVAC systems can usually take more than 10 years. And so this is not being critical of the performance or the benefits of how conventional geothermal systems are installed. It's just by nature of the process and cost of it, they take a long time to recover that investment. So a question my partner and I asked ourselves 3 years ago when we first got into geothermal was, do we really need to drill so deep? Especially considering that ground temperature is stable all year round by that about 30-foot depth. And so that's the key to the new approach we're taking at InnoviaGEO, which is to develop geothermal solutions focused on softer, shallow grounds so we can greatly reduce the time, cost, and mess of installing a geothermal system. And so by focusing on these shallower depths, there's a couple of benefits that arise. And so we can install these systems a lot faster because we can repurpose foundation construction techniques to be able to install them at faster and cheaper rates. So at these shallower, softer depths, that's the range at which foundations are built, and working with foundation contractors, we can use their techniques to be able to get those installed, a lot faster. And so second as well is scalability. And so we can actually use the foundation industry itself to scale. And there's a heck of a lot more foundation contractors out there than there are geothermal drillers. And now in Ontario, there's quite a bit of activity in new builds, large projects with geothermal. And so the drilling capacity is getting maxed out essentially. And so there's a restriction and constraint with the number of drillers able to drill those 850-foot holes in the ground. The third piece here is less risk. And so by focusing on these shallower depths, we can avoid some obstructions and challenges that are possible to encounter at those deeper depths. And specifically, it's underground aquifers and then gas pockets as well. And this is particularly relevant to the region of Waterloo because of the Source Water Protection Act and drilling depth restrictions that exist in certain regions because of protecting those groundwater resources. And so here's a map from the region of Waterloo showing the groundwater and source water protection zones within the region, which is those areas in pink there. So it's quite a large, part of the region, Guelph as well, but other parts in the province as well. We're seeing this crop up, and it's preventing those that want to install an efficient geothermal system. It's preventing them from doing that because of those depth restrictions. The other challenge that has encountered the industry before is gas pockets. And in particular, in our area, they're encountered more frequently in the shale formations around Lake Ontario. And so there's been instances before that the gas pockets haven't been properly managed, and they've led to problems before. So, not something that is overly common, but there have been issues before, and there's instances where they haven't been properly managed and have led to houses getting evacuated in Oakville and other cases of challenges as well. So what are we doing? So what we're really doing is, our view is that there's a missing technology here in the realm of geothermal technologies. On the one end of the spectrum, I've talked about the vertical closed loop system, those deep geothermal wells, up to 850 feet deep these days. Very scalable because you can, almost install them anywhere, but at a very high cost. On the other end of the spectrum, we have horizontal loops where a large trench is dug, and those pipes are just laid out in a trench, maybe about 7 to 10 feet deep. The Waterloo North Hydro head office has a large horizontal system that services a large area of the office and service building there. But you need a lot of space for that. And so scalability is a challenge. And then as well, open loop systems where water is taken directly from a water source in the environment, oftentimes an underground aquifer. Very cost effective, but very difficult in terms of permitting and also finding locations that have that suitable groundwater resource. So what we're doing is focusing on developing technologies where we could install them in as little as 50 feet deep within that soft soil, so we can improve the economics of a closed loop system. So with our approach, we've got two technologies that we're developing. Our geopiles, what they do is they integrate geothermal functionality into steel foundation piles. So when you're installing your building, we can piggyback off of that infrastructure that's already going in to your building, and we can integrate that geothermal functionality into it, and you can get a very cost-effective geothermal capacity from the very foundation of your building. The second technology, our geocolumns, are standalone geothermal systems, but they're designed to be installed using these repurposed foundation construction techniques and installed at rates 3 to 5 times faster than conventional drilling methods. And we're targeting that 50-foot depth because at that 50-foot depth, we can scale across a large region. So here's a map of North America with the areas in green showing the areas where bedrock is at least 50 feet deep, and our approach and technologies are technically feasible. So, kind of zooming into Ontario here, sort of southwestern Ontario has some good ground conditions for us. we wouldn't be able to apply our technologies in Eastern Ontario, where the Canadian Shield is, and that bedrock is really close to the surface. So our approach isn't viable everywhere, but viable in a good number of locations. And so we've been developing our technology in collaboration with Toronto Metropolitan University, which is formerly known as Ryerson University. And so we've had a 3-year research collaboration with TMU, and have so far led to 2 successful master's theses, and also 2 publications in peer-reviewed journals. And also we've got a first patent application that we recently submitted as well as a team there. And this research collaboration really arose because there's a lot of knowledge out there on how to design a geothermal system using the traditional approach of drilling those, several 100-foot wells in the ground. And there's a lot of knowledge on how to build a horizontal and an open loop geothermal system that exists. But what we found was, with our approach, that understanding and design knowledge didn't exist. So we had to go sort of the hard science research approach to begin developing that knowledge and understanding. And through our process, we were introduced to Waterloo North Hydro, and they were, very happy to host our first full-scale pilot of our geopiles. And so it's installed at the Rush Transformer Station next to Regency Park. And so that facility was installed towards the end of 2020 and operational beginning of 2021. And I tell everyone I know that week very well, because my daughter was also born the same week that we were commissioning the system. So it was, I think, a week I'll never forget for a number of reasons, and also the little hours of sleep I got that week. But we were able to get that system installed. It consists of 8 steel piles, 50 feet deep, and the design rating, it's a 2-ton HVAC system, give or take, for its design rating. What's great about this facility as well is that there was a conventional vertical geothermal loop that's been installed and operating at that facility since the mid-90s. And so we've been able to design our system to be able to do side-by-side testing and operate the system in conjunction with the conventional vertical geothermal system there as well. And we're seeing that there could be applications where we can actually combine these 2 technologies together for some benefits there. And so it's been operational for just over a year. We're working with the university now to go through a testing program. And so we've gone through part of winter, we did last summer, and then we did some testing this past winter. And then we're doing some more, just started up doing some more testing with the hot weather that's recently arrived. So we're starting our next phase of cooling testing. And so a question that I'm sure is on your minds is, how do we get good performance in a geothermal system that's only going 50 to 100 feet deep, as opposed to these systems that have to go hundreds of feet deep? And so there's a couple of factors here, but it boils down to the principle of low flow and a high volume system that we've developed here. And so in a conventional geothermal system with the small pipes about 1 to 2 inches in diameter, the principle is you've got to push that fluid through quickly so that it encourages mixing of that fluid to exchange that heat with the ground. So our system is designed a little bit differently, where we have a much larger pipe, greater than 4 inches in diameter, and our design principle is to actually trickle that fluid into that larger pipe so that it spends as long as possible in the ground to exchange heat that way, rather than pushing it through and encouraging that mixing. And so with that design change, what we do is we have a much larger surface area in contact with the ground per unit depth. So we're able to get more heat and exchange more heat with the ground per depth than a conventional geothermal loop. The other piece there that's very important is this usable thermal storage capacity, and that arises because of the fluid volume in the system. So if you think of a 4-inch pipe compared to a 1 to 2-inch pipe, there's a lot more fluid in the system. And what we're finding with our testing is that we can utilize that fluid as a heat battery and a thermal battery. And I'll get more into details later on about that. The other piece here as well is with our low flow system design, we have a reduced circulating pump power. So the energy needed by the circulating pump to get that fluid through the system to actually exchange that heat is quite a bit less. And so our system at the EB-Rush pilot, the circulating pump power requirements are about a quarter, third the circulating pump power requirements of the conventional loop that's there. And so the property that gets us really excited is this thermal storage property of the geopiles and geocolumns. And so in a conventional geothermal loop, what happens is that you're exchanging heat on a steady state basis through the surface of that pipe. With our geopile and geocolumns, we still get that effect of that heat transfer through the surface of the pipe itself. But then if the system is turned off or at a lower stage where it's below that steady state heat transfer rate, what happens is we can actually use the energy in the fluid itself and then recharge it. And so that we're getting that temperature at a better state so that it can operate more efficiently and provide the heat pump with a more stable operating temperature. And so here's an actual result from testing we did last summer where we did exactly that. So over 3 days, and they were 3 pretty warm days, we turned on our geopile system and let it operate at maximum during the peak hours of the day. So probably around noon to about, I think it was about 8 or 10 p.m. in the evening there. And then we shut off the system. And what we can see here is this is the entering water temperature to the heat pump. And so at the moment we shut it off, we see that that temperature is dropping. And so what's happening is that the heat that's accumulated within that fluid, it's still dissipating that heat with the ground naturally because there's a temperature difference that exists. And so we're not having to put an energy input into the system to have that happen. It's just naturally happening because of that pull towards the stable temperature of the ground. And then what we did was the next day, we did the same thing. We turned it on around noon, let it operate for that period of time, and then we see that effect still happening. And so this was a controlled test to test this thermal storage effect, but it has real implications for the efficiency of an operation of a system. And so what we ended up doing was a few days later, we did a similar test with the conventional geothermal loop that was installed at the station there. And so here's the results that we have. And so these 3 lines here was the operation of the geopile system. And so we can see that the entering water temperature, we were able to keep that in a pretty tight range. So we were able to keep it, I think it was about just less than, or just maybe over 13 degrees Celsius. So that was the range that we're able to operate the system at. With the conventional loop, when we turn the system on and it on to maximum, what we can see here is that because the fluid volume in the system is substantially less, that temperature increases pretty quickly. And so it rises up pretty quickly, and then it leveled off and operated at about, I think it was about 21 degrees Celsius consistently at that steady operation stage. And so that's a pretty big difference. And when we look at the efficiency curve of the heat pump, what we can see is that by operating and keeping that entering water temperature in that tighter range, we're actually able to operate the system about 20% more efficiently than the conventional geothermal loop. And this is part of the testing we're going to be doing over the next year, is really trying to understand this thermal storage property, especially considering a building heating and cooling load profile is never really too consistent. And so all our systems are designed to meet our, peak heating and peak cooling days. Just like a power system, you have your base load generators and your peaking power plants. right now, all our systems are designed peaking power plants because we need to meet those peak, cold days and hot days like today. But all the other times of the year, you're operating the system at part load. And so that property and being able to use this thermal storage property, we can start, and we'll be starting testing control strategies around, maybe prepping a system for a heat wave that's coming so that we're able to keep it in a more efficient range, over a couple of days. Or maybe it's just operating the system more efficiently during peak electricity time. But when we start thinking if we could multiply this 20% energy efficiency savings with energy price savings as well, with the difference between on-peak and off-peak pricing, then we can actually maybe affect your utility bills even more. And so in terms of applications, where we're looking at, so we're really focused at our approach being viable for mid-rise structures. And so for a high rise, you're probably going to need, if you want a geothermal system, you're probably going to need to drill those deep, couple 100-foot wells, because you need that ground contact to get the heating and cooling capacity you need to meet that higher building. But for low and mid-rise structures, where there's a little bit more of a footprint, maybe a yard, a driveway, our approach, we're really looking to focus on that segment of the market. Also because it's tougher and economics are tougher for conventional geothermal with low and mid-rise structures. For district systems, so systems, for example, that service multiple buildings, we're really interested, and we'll be doing some testing on using our technologies as a peaking capacity. So what that means is that you can shrink the amount or reduce the amount of conventional deep drilling you need to do, and be able to utilize our approach and our technologies in conjunction with that system. And we can also use our technology to help maintain the loop temperature controls and maintain those temperatures. And so a challenge actually with conventional geothermal systems in our climate, in high rises, is actually the buildings tend to be cooling dominant, which is a little bit sort of counterintuitive considering the winters we have. But with heat rising and a lot of the building practices with using a lot of glass for high rises, there's a lot of heat accumulation that happens within those buildings, and also with the density of folks in there. And so there's a need to actually dissipate excess heat in order to have the system balanced through the year. So we're looking at using our technologies as a way to help balance and maintain that temperature control. The other approach that is probably a little bit further off, but we're really interested in is hybridizing our technology with air source heat pumps to improve efficiency and resiliency of those systems as well. So air source heat pumps, you're probably familiar with them. So they're exactly like a geothermal heat pump, but they move heat with the outside air. So an air conditioner is just a subset of an air source heat pump. Air source heat pumps are just reversible, air conditioners that can also provide heating. The challenge is when it's really cold outside, their efficiency really drops off to the point where in extreme sort of cold conditions, usually around -20, their efficiency is pretty much on par with even maybe a little bit less than electric baseboard heaters because of the power you need to operate those fans. And so hybridizing with our systems to provide a peaking capacity and also a buffer, we're really interested in looking at combining them together to provide a sort of a system that can work and make use of the best benefits of both technologies. And so in terms of our next steps and plans, so we've got the EV Rush pilot that we're doing our testing on right now. We're going to be installing a full-scale system in a model home with a pretty large developer with the intention of getting that installed towards the end of this year. And so proving it out on a home scale. And then from there, our plans are to conduct larger pilots, mid-rise and larger pilots, maybe up to about 8 stories for a residential structure over the next 1 or 2 years. And our objective is to be able to offer the geopiles and geocolumns on a turnkey design, build, operate basis to full commercial projects by 2025. Sooner if we can do it sooner, but that's our plans of being able to sort of stepstone along the way of larger and larger projects. So who we are, so my background, as Andrew had mentioned before, comes from the renewable energy development sector. My partner's background comes from the construction sector. So my partner Jim has worked over 30 years in the construction sector, including running a division of Ellis Dawn Corporation, a large construction company, for about a decade. And then we've got a research collaboration with Dr. Seth Dworkin, who is a professor of mechanical engineering at Toronto Metropolitan University. And our goal is to get the future to be cleaner and brighter with geothermal, and we think geothermal is that missing piece to the decarbonization puzzle for the built environment, where the way to think of it is, a geothermal system can multiply, every renewable electron we use to operate that system. So the efficiency of a geothermal system, it can move 4 units of heat, from the ground into a building. Then every electron of solar or every electron of wind that we use, we can actually multiply it by 4 to be able to provide that heating and cooling and solve that biggest piece of the pie in our homes and buildings. So with that, I guess it's the finish or end of the formal presentation. So very happy to answer any questions that folks might have.